Hello everyone. So in this video, we are going to see this particular question, like why do we need reactive power compensation in power system? Okay. So to answer this particular questions, we will see a kind of analysis. What will happen if there is any load that the load is demanding huge reactive power? So in that case, what are the difficulties the power system will face? Okay. So let me take one example for that, and let's say. Um, I have a synchronous generator with me, and that synchronous generator is connected to a bus, and that and we have a transmission line that has a reactance. Let's say this reactance has X, and here I have some load is connected. Okay, for this to understand this behavior, like how what will happen if there is a uh, there is a load that is demanding more reactive power, or there is a load that is delivering reactive power into the power system, then what are the scenario that can happen? Okay, so let's say my terminal voltage here, it is VT at an angle 0, and this is my internal EMF of synchronous generator. And let's say for case number first case, I have the load, it is a purely inductive load. That means the current that is flowing through the load, uh, we can say for purely inductive load. Okay, purely inductive load. As you know, the inductive load consumes reactive power. Okay, so if my load is purely inductive, I can write the load current IA is equals to IA at an angle of minus 90 degree, right? Because it is a purely inductive load, so my current will lag the voltage by 90 degrees. So my reference voltage is VT at an angle 0, so this is how it will lag. Now let me calculate what will be the internal EMF equations. Okay, so if you write the KVL, then you will get uh, EF bar is equals to VT at an angle 0 plus uh, JX, okay, and the current IA minus 90. Now from this particular equation, you have this J contribute to plus 90 degree, and we have this minus 90 degree. So plus 90 minus 90, it will be simply 0. So I can write EF VT at an angle 0 plus IA X and 0. This 0 is because I already explained plus 90 and minus 90, so it will become 0. If you see this particular equation, the angle associated with these two quantities are 0. Okay, so that means this is a simple scalar addition, not a vector addition. Okay, because these two quantity VT, which is at reference phasor, and IAX, which is also at reference phasor 0. So they are the you can say they are the scalar addition. So I can just remove the bars and all. I can just simply write the simple equation VT plus IXs. Okay, so this is how. Now let me rearrange the equations. Maybe I can write VT is equals to EF minus IAXs. Okay. Now let me draw the VT versus IA graph. VT versus IA graph. Um, let's say this is my y-axis, this is my x-axis, this is my IA, this is my load current, and this is my terminal voltage. And from this equation number 1, you can see whenever the current IA is 0, the EF and VT are same. So here VT will be simply EF, and this particular equation has negative slope. As you increase the current, the terminal voltage will simply decrease, and it will follow the linear curve. It is a linearly decrement equations. So this is how it will decrease. And maybe we can write it, draw it more proper. Okay, here, and at this point your VT is 0, and when VT is 0, from this equation 1 you can write IA is equals to EF by XS. EF by XS. Now one thing is pretty sure from this particular analysis is, let's say you have this lagging load and you're varying this lagging load and you're drawing more lagging current. In that case, your terminal voltage will simply decrease, and there will be some cases that the terminal voltage may collapse also. So this particular scenario will happen when the load is purely inductive, or we can say ZPF, zero power factor lagging load. Okay, zero power factor lagging load. So in that case, your voltage will collapse, and it is not a good phenomenon, because you have an entire power system network, let's say, and as per the IEEE standard, your voltage variations in a particular bus should be from 0.95 per unit to 1.05 per unit. So your voltage variation must be in between these two ranges. So if there is any load, or there is any excess amount of reactive power demand from the from the network, then there will be reactive power imbalance in the system, and the voltage of the buses will decrease basically. So if I say that what is the fundamental behind this voltage collapse and all, basically this voltage collapse or voltage instability issue arises because of imbalance of reactive power into the power system network. If there is any excess amount of reactive power, then the bus voltage or the voltage at buses will increase, and if there is a consumption, if there is more consumption of the reactive power, then the voltage will simply reduce. We will see the case number 2 when the load is purely capacitive. Okay, so let's say we have this purely capacitive load, purely capacitive load. Okay, purely capacitive load. In that case, your IA will simply IA at an angle of 90 degree, because it leads the voltage by 90 degree. Okay, so if you write the KVL equations, so you will get EF is equals to VT at an angle 0 plus JX IA at an angle 90 degree. Now this J will contribute 90, and this is also 90. So 90, 90, 180. So 180 degree, you can simply write negative sign. Okay, EF. So VT at an angle 0. This is negative because of 180 degree angle IA XS. Right. Okay. So let me, so here I have like taken the effect of J and this 90 degree in the form of this negative sign. Now I have this angle as 0 degree, so all are in the same phase, so this is a scalar equation only. EF is equals to VT plus minus IA XS. Now let me rearrange the equations. VT is equals to EF plus IA XS. Okay, let me draw this one also. Now, let me draw the, maybe I can draw the terminal voltage waveform for both ZPF lag and ZPF lead. So it is my terminal voltage. Here we have seen from the previous slide, like the for ZPF lag, your voltage is simply dropping, and here the current is EF by XS. Okay, and here your terminal voltage is EF. Now if you see this particular equation, equation number 2, it has positive slope, and when IA is equals to 0, then your terminal voltage is EF, so it is satisfying it. As you increase the current, your VT will linearly increase. Okay, so your VT will linearly increase, and we will see some things like it will increase like this. Okay, and there will be increment in the terminal voltage. Now if I'm calling this EF is at 1 per unit, then there will be some condition my when my VT will be 2 times the EF. That means maybe my terminal voltage will increase up to 2 per unit. Okay, so what will be the scenario? So at 2 per unit, my VT is simply 2 EF. So 2 EF is equals to EF plus IA XS. So that is IA is equals to EF by XS. So same current. You are also getting the same current. That means this particular graph is for ZPF lead and it is ZPF lag, this the pink one. So you can see um, your bus voltage variations or terminal voltage variation of a power system network, it totally depends on the imbalance of the reactive powers. Okay, and this is that is the reason you have to come up with some reactive power compensation solution. Okay, for example, if you have, let's say, if you have this particular lagging load, let's say it is your ZPF lag, not ZPF lag, maybe some simple lagging load if you are taking, then to compensate the reactive power, maybe you have to connect a compensating device, and that compensating device you have to analyze like what will be the rating of this capacitor if it is a inductive load, how much reactive power it is demanding, and according to you have to design this capacitor. Or you can also think like there is one more case, if my load is capacitive in nature, in that case maybe you have to connect a reactor parallel to the load, and this reactance value you can also calculate from some mathematical steps and all. Basically, in practical scenarios, most of the loads are in lagging in nature. So the compensating device you have to connect in power system network, that will be capacitive in nature. Okay, but there is a one more case, something called Ferranti effect in power system. In that case, your terminal voltage will increase. So in that case, you will have to connect a shunt reactor to minimize the terminal voltage or the bus voltage and all. Okay, we will discuss all of these things later, but as of now I think it is clear like why this reactive power imbalance and this voltage instability issues are occurring, and why do we need this reactive power compensation. Okay, so that is the reason. It may lead to over voltage, it may lead to under voltage. It is the like it create a voltage instability issue or voltage collapse. And one more thing, like let's say you are having some inductive load. Okay, you're having some inductive load, maybe some RL type of load, and this particular inductor will definitely require some kind of reactive power and all, because it will absorb reactive power. So for that, the load will demand the current from source. Okay, so what will happen if the load demand some current and there is no compensating device, that current will definitely come from the source side. So the current magnitude will increase, that will lead to more losses in the transmission line. Okay, the transmission line losses will increase if there is no reactive power compensating device. Okay, so simply the transmission line losses will increase. And once you have this compensating device parallel to the load, then your input power factor will also improve. Input power factor improvement means you can deliver more amount of more amount of active power. And so basically this is our goal, right? We must be able to deliver more active power, and such that we can get more profit and all. So this reactive power compensation will improve the power factor. It will decrease the transmission line losses. Even this reactive power compensating device also improve the voltage regulations. Okay, and simply this reactive power compensating device also increase the system stability from all the aspects, because if there is any collapse in a particular bus voltage, then that collapse may lead to some what do you say, some subsequent other reactions also. Like if there is a collapse in a bus at a particular bus voltage, then that collapse may can lead to frequency instability issues, rotor angle instability issues. So they are all are interlinked. So we must have some kind of compensating device in power system network, but we have to analyze first what is the reason behind that. Okay, and I hope it is clear now why this reactive power compensation is required in power system. If you have any doubt, you can ask me in the chat box. Yeah, thank you.